Let us consider a few examples for simple harmonic motion. One is the concept of physical pendulum. The concept of physical pendulum. So, let us take up an example of physical pendulum. Already we have taken up the concept of simple pendulum, which of course will be finding a bob at the end of a string, which will be suspended freely, and the oscillations of the bob are said to be simple harmonic. Similarly, when we consider a body like this, for example, I am taking a body this way, which is suspended at this point O vertically this way. Like a calendar or any other portrait, we are just hanging that one to the wall. And of course, I consider this is the point where the effective center of mass of that particular body is now observed. And the distance to this particular center of mass, I consider that distance as d. Now, when I just move this one aside a little, and if I leave it, then even it also oscillates simple harmonically like this. So, this type of a body, any body, there is no restrictions for that. Any body, whichever is suspended with respect to a fixed point and made oscillated to and fro with respect to the mean position of rest, such body now can be treated as a physical pendulum. Now, in this particular example, how can we show that this is simple harmonic oscillation? The oscillation of this pendulum is simple harmonic. How can we identify that one? And secondly, what is its time period of oscillation? What would be its frequency of oscillation? Likewise, what would be its angular frequency as such? These are the formulae one has to remember as far as physical pendulum that is concerned. Imagine for a while the same body. Now, I have just pulled it aside with respect to the vertical. It's now, this is the point called center of mass, I said. This is the distance we have already taken up. It has now been pulled aside by making an angle theta here. Then definitely one can understand its weight that is going to act downward over here. Now, when weight is acting downward, what is going to be the restoring force that is acting on this pendulum to bring it back to normalcy? When this body is being moved aside by an angle theta and left over here, it definitely oscillates. One can now understand in this case, mg sin theta is responsible for bringing this body to its normal position of rest. And this d is the perpendicular distance what exactly is acting over there at the center of mass. So, what one can understand here is what would be the restoring torque. What would be the restoring torque that is acting on this body to bring it back to normalcy? Restoring torque, of course, being opposite by direction, we can directly take a negative sign there. And mg sin theta is the force and perpendicular distance being d there, I can write directly mg d sin theta. That is the concept. But one can directly understand in this particular case, what is this value of mg sin theta? mg sin theta is going to be the force responsible for bringing this one back to normalcy. And d is the perpendicular distance over there, torque whenever we consider. Directly one can take up force into perpendicular distance, the concept there. Therefore, we can write the same equation like this. So, the torque that is acting on the system is mg into d sin theta. If I consider theta is very small, then I can directly write sin theta nearly equal to theta. In fact, every one of us we know limit theta tends to 0, sin theta by theta is equal to 1. So, sin theta can be written as theta. Therefore, the restoring torque over here, that now becomes mg d into the value of theta. When I consider this is the torque, in true sense we know torque is going to be I alpha, where I is moment of inertia and alpha is angular acceleration of this body. That means, what kind of harmonic motion it is now to be called? It is angular simple harmonic motion. So, the moment I write torque as I alpha here, these two are supposed to be equal. So, what can I write now from this one? I alpha is equal to mg d into minus theta you can write. In other words, alpha is equal to mg d by I into minus theta. But in fact, every one of us can directly understand angular acceleration is directly proportional to angular displacement in opposite direction. That is the principle for angular simple harmonic motion of a body. So, what one can understand from this one? We directly know, directly we can take up one point. What is that? Alpha is equal to omega square into theta with a negative sign. Therefore, what would be the value of omega now? Omega becomes root over mg d by I. What is this omega called over here? This is what we call it as angular frequency. So, angular frequency of this physical pendulum. What is the corresponding formula for that? It is mg d by I. Similarly, what would be the time period of its oscillation? Time period, if I want t, it can be written as 2 pi by omega. That is the basic concept, basic formula for us. So, we can rewrite the same 2 pi into, right, root over I by mg d. This is the formula for time period. And if at all we want, what would be its linear frequency? Linear frequency, we can take it as reciprocal of time period, which can be written as 1 by 2 pi under root mg d by the value of I. But what is this value of I here? Here I stands for moment of inertia. The rotational inertia of the body, what is called as moment of inertia? We directly take that one as I there. So, depending on the shape of the body, depending on the axis of its rotation, shape in the sense the mass one has to consider, and depending on the axis of its rotation, one can estimate what is the formula for I. So, in each equation, we are having this moment of inertia term. That I is of course moment of inertia. Every one of us we know how to calculate the value. Basic equation is mk square. M is the mass and k is radius of gyration, what we call it. Now, as an example, when we consider the very first example as a circular ring, when I just take a circular ring here, this is now fixed over here, or it is now put over a nail like this, and it is now oscillated. That also becomes a physical pendulum, and this being the center of mass point of the circular ring, this distance now becomes its radius. Then for the circular ring, about this point O as the axis, what would be the moment of inertia? According to parallel axis theorem, one can directly write mr square plus mr square. That now becomes 2mr square. That is the moment of inertia for a circular ring. Along the axis passing through its center of mass, it is mr square. Plus mr square applying the parallel axis theorem. Therefore, this becomes 2mr square. That is the formula for moment of inertia of a circular ring. Suppose if I consider the same as a circular disc. When I consider the same body as a circular disc, then what would be the moment of inertia? It is mr square by 2 plus mr square applying parallel axis theorem. This now becomes 3mr square by 2. This formula we can write in each of the equations to calculate omega or t or n for a circular disc when it is fixed like this again. Exactly in the same manner for a uniform rod. Suppose if I consider the body as a uniform rod like this, this is now fixed over here at O. It is now made oscillated once again like this. That also becomes a physical pendulum. What would be the formula for moment of inertia in that case? It will now be ml square by 3, where L is the total length of this rod and m is the mass of the rod. So, when uniform rod is taken, I is equal to ml square by 3. For circular disc 3mr square by 2. For circular ring 2mr square. So, that way depending on the mass of the body considered and the axis with respect to which the body is being oscillated. That is very important. Considering that axis, then only we have to estimate what is the distance over there. Thereby, considering that mass and the distance over there, one can estimate what is moment of inertia in each of the cases like this. So, this is one of the wonderful applications for this angular simple harmonic motion in this topic called oscillations. Let us take another example, that is torsional pendulum. How to just calculate the time period of oscillation or frequency or angular frequency? And most of all, what one has to understand in this case is, how can we say that the oscillations of this torsional pendulum are harmonic? That too simple harmonic. What is this torsional pendulum first? A uniform rod will be like this. To this rod, a circular disc will be attached at the other end. This is a uniform rod, and here we will be having a circular disc that is attached. Now, what one can understand out of this one is, when the system is hanging like that, when I just rotate this one a little, causing some torsion in the rod, and if I leave it, then this total disc now oscillates this way. This is what actually is the concept one has to understand in the case of a torsional pendulum. Now, the first concept here is whether these oscillations are simple harmonic or not. That is the first concept we just have to decide. So, for that, when it is just rotating and leaving like that, if I consider torsional constant of the rod is C and angle of rotation is theta, then we directly can write the restoring torque tau now becomes minus C theta. So, this is the basic equation one has to remember in the case of a torsional pendulum. But all of us we know well, torque is equal to I alpha, where I again is moment of inertia, alpha is angular acceleration. Now, equating these two, we can write now C theta is equal to I alpha, that implies alpha will be C by I into minus theta. This is exactly similar to alpha is equal to omega square into minus theta, like this is the equation or the condition for simple harmonic motion of a body. When I consider this one as a condition, is it not similar to this now? So, in place of omega square, what do you have here? It is a C by I. C is torsional constant and I is moment of inertia of the disc what we are having here. So, when you write this one, therefore, omega becomes under root C by I. This omega is now called as angular frequency. That is what we call it as omega. And of course, what is the value of I for a disc? You can directly understand it is mr square by 2. We can write mr square by 2 for a disc along the axis passing through its center of mass perpendicular to its plane. Of course, if you want the value of I to be substituted, you can substitute that way. Otherwise, you can leave it like this, omega is C by I under root. And what would be the time period in this case? When we take time period t is equal to 2 pi by omega, 2 pi under root I by C we can write. And what would be the frequency thereafter? What would be the frequency? N can be written as 1 over time period, reciprocal of time period, which can be written 1 by 2 pi under root C by I. So, one should understand here C being the torsional constant, I being the moment of inertia. The time period of course becomes 2 pi root I by C. Angular frequency becomes under root C by I. Similarly, linear frequency becomes 1 by 2 pi under root C by I as such. This is another example one should understand from which that the oscillations of this torsional pendulum, they are also simple harmonic, but they are the example for angular simple harmonic motion. That is the point. The concept of torsional pendulum itself we use while deriving an expression for the time period in the case of a vibration magnetometer in magnetism topic. One should understand in the case of a vibration magnetometer, the torque that is acting on the bar magnet over there will be MBH sin theta. BH is horizontal component of Earth's magnetic field and capital M is magnetic moment and theta is the angle of its oscillation. Angular displacement we can call it in other words. But when theta is very small, this can be written as MBH into theta, since sin theta is very close to the value of theta when theta is small. But the same torque we can write it like as I alpha as well. I is a moment of inertia of the magnet. Usually magnets are rectangular by shape. So m into L square plus B square by 12 is the formula for magnet, this one moment of inertia. M into L square plus B square by 12. So if you just equate these two values, I alpha now becomes MBH into theta. Since this is restoring torque, we put a negative sign before, and therefrom I can write that alpha is equal to MBH by I into minus theta. This directly gives you that omega is equal to under root MBH by I. So this is the angular frequency of the oscillating magnet in the case of a vibration magnetometer. Similarly, what would be its time period? Suppose if I write time period T now becomes 2 pi under root I by MBH. That is the concept. And of course, the frequency part, whenever we consider that n is equal to 1 by 2 pi under root MBH by I. So looking to this particular equation, one can understand that again these oscillations of the magnet in the magnetometer are simple harmonic by nature. Angular simple harmonic motion it is. Thereby, what is the frequency, what is angular frequency and what is the time period of the oscillating magnet in the case of a vibration magnetometer, whenever we want to calculate, these are the three different formulae one should remember. And what is capital M over here called? Capital M, we call this one as magnetic moment. And what is this magnetic moment? It is pole strength into the length of the magnet. And in this case BH, we call it as horizontal component. Horizontal component of Earth's magnetic field. Earth's magnetic field. That is the concept. And what is this I now to be called? Its moment of inertia. Moment of inertia of the magnet. The bar magnet, what is being used there. What is the basic equation for moment of inertia? It is m into L square plus B square by 12. But one should understand generally in the case of a bar magnet, breadth will be negligible when comparing to the length part of it. If they say the breadth is negligibly small like, then we can rewrite the same equation as ml square by 12. So using that equation we can calculate I, that's moment of inertia. Horizontal component of Earth's magnetic field will be given over there, and the value of magnetic moment will be provided to us in the problem. So when you know those values, directly one can estimate whether the time period is asked or linear frequency or angular frequency thereby. This is one more application one should remember in terms of angular simple harmonic motion. Let us consider another example for simple harmonic motion. where a simple pendulum is made oscillated inside a liquid. The density of the liquid will be provided to us. For example, this is simple pendulum oscillating in a liquid of density rho. That is the concept. A simple pendulum oscillating in a liquid of density rho. Let us just consider this is the case. This is the simple pendulum. Its mass is given as m and length is mentioned as L. Now this total pendulum is inside a liquid like this. The density of this liquid is provided to us, that is rho. Now this pendulum is brought aside this way by making an angle theta with the vertical, and it is now oscillated. Then what are the forces they are going to act on this bob? One directly can understand that weight will be acting downward, which of course we can call it as mg. Due to the density of this liquid, there will be a buoyant force that is going to act on it. That's called buoyant force. What is that buoyant force over here? That can be written as V rho g. V for volume and rho the density of that liquid what has been considered, and g is acceleration due to gravity. It is in fact buoyant force also is equal to mg only. But while taking up mass, it is volume into density we are considering, that's all. So the buoyant force is acting upward and weight is acting downward. Then what would be the effective force that is acting on the system? That in other words, I write the same this way, what is going to be the restoring force that is acting on the bob? That restoring force I can write this way as mg minus v rho g sin theta. But you definitely can understand when this angle is very small, and if I take this displacement of the bob as x, then I can write sin theta as x by L. So L is the length over there of the pendulum and x is the displacement of the body. Directly I can write it like that. Therefore, the restoring force that is acting is now minus of mg minus v rho g into the value of x by L. That is the concept. But when we know this is the restoring force, what would now be the acceleration of that bob inside the liquid? So we can write this implies acceleration now becomes restoring force divided by mass. So what would be that value now? Minus g minus v rho g by m into x by L. That is the equation what we can get for acceleration. Same equation I just rewrite in a different manner now. Acceleration A is equal to g minus v rho g by m whole divided by L. into minus x. So, x is the displacement and a is acceleration. Are you not observing that acceleration is proportional to displacement taken in opposite direction? So, every one of us can directly understand by looking to this equation, that equation refers to simple harmonic motion of the body. So, surely even if the pendulum is made oscillated inside any liquid also, it will be having the same simple harmonic motion in that liquid. Therefore, what can we write now? The angular frequency of the body which is in simple harmonic motion. This angular frequency, now omega, can be written as under root. Directly you can write g minus v rho g. So, the angular frequency of simple harmonic motion of that bob inside the liquid now becomes g minus v rho g by m whole divided by L. So, when angular frequency of the bob is this much, what would be its time period? Time period t of course can be written like this, 2 pi under root L by g minus v rho g by m. Exactly in the same manner, what would be its frequency of oscillation? That is n, which is reciprocal of time period 1 by 2 pi whole under root g minus v rho g by m divided by L. So, when you just take a pendulum is made oscillated inside a liquid of density rho, then first and foremost this equation tells us the oscillations are simple harmonic. And second, looking to that equation, one can write a formula for angular frequency, for time period and for linear frequency of that pendulum which is oscillating inside the liquid. So, this is another example what we are having as far as simple harmonic motion that is concerned. Let us take another example for simple harmonic motion. Oscillating liquid in U-shaped tube. So, oscillating liquid in U tube, that is the one what we are taking up. Say for example, there is U-shaped tube like this, uniform tube it is. Initially, the level of liquid in both the limbs is same. This is all liquid now, what we directly can understand. Since both the ends are open to the atmosphere, whatever atmospheric pressure that acts on this one, same atmospheric pressure that acts even on the other one as well. Therefore, both the liquid levels are going to be equal. They will be the same. But what I have done in this particular case is, I just have made the liquid in one of the limbs go down a little from the initial level. That means it has some air has been blown into it to compress the level of the liquid. Then naturally that level has come down to this. So, you definitely can understand now what is happening here. Earlier level was till this extent, now it has come down Now you can definitely understand it has been compressed by Y. Then automatically that liquid rises in the other limb now. Once again you can understand now, when this is the level of the liquid, this was the original level, it has now been expanded or come up to that particular distance Y like this. So one can understand in this case, when we just have compressed this liquid by blowing some air or something like that in this, then the level of liquid rises here by the same value Y. That means presently this is coming down by Y and that is going up by Y, means the total distance or the total height to what extent it has gone up will now be 2Y. So what one has to understand in this particular case is, whatever the restoring force that is now caused by this level of height to Y, that's what we just have to calculate. So one can understand here, restoring force due to the liquid level or liquid column of height to Y, that restoring force now can be written as pressure into area of cross section. Now in this case we are considering that area of cross section of this tube as A, and this pressure we now can write into area of cross section. Cross sectional area, since it is restoring force, we just put its sign as negative. Now I can directly understand pressure due to this liquid column of height to Y, it is H rho G. So one can understand in this case pressure becomes 2Y into rho into G, that is H rho G, that will be the pressure, into the area of cross section of this one. If I consider that as A, 2Y rho G into A, that gives you the total restoring force that is acting due to that liquid column. When this is restoring force, what would be the corresponding acceleration of that oscillating liquid? What happens in this case? This level comes down, this goes up, this comes down, this goes up. Continuously the liquid used to oscillate to and fro with respect to the mean position of rest, which of course can be taken as simple harmonic oscillations in this case. So what would be the acceleration now? It is restoring force divided by the value of mass. So we can write this one like 2 rho G A by M into minus Y. Again try to recollect, acceleration is directly proportional to displacement taken in opposite direction. This is just similar to omega square into minus Y like. That is the basic equation which gives you simple harmonic motion of that body, in this case the liquid. So you can now understand what would be the value of omega. Now omega becomes under root 2 rho G A by M. That is the concept what one has to understand here. So if you take 2 rho G A by M, that is angular frequency which can be written as omega. What would now be the frequency? This implies time period is equal to 2 pi under root m by 2 rho g into A. You can even rewrite the same this way, and the linear frequency n is equal to 1 by 2 pi under root 2 rho g A by m. So, when you just take the oscillating liquid in U-shaped tube is now making simple harmonic oscillations, what is going to be the basic equation which tells us that the oscillations are simple harmonic? This is the one. After getting this value, what is its angular frequency, what is its time period, and what is its linear frequency, everything of course we can calculate by considering the basic equations there. So, this is another example where we can observe simple harmonic motion once again. Let us consider one more example, like oscillations of a floating body. Oscillations of a floating body. So, let us consider this way, there is a body which of course is now floating on water like this. A part of that one is outside water and a part of that one is inside this water. It is now floating like this. Now, when this body is just floating like that, what I do is, I just push this one a little into the water and leave it. I just apply some force normal to its plane, the topmost plane of it. Directly I just compress it, I just push this one into water and leave it. Then if you observe carefully, that used to oscillate in the vertical plane simple harmonically. That is the concept. So, the oscillations of this one are supposed to be simple harmonic. That we have to prove it first. The second concept is, what would be its time period of oscillation? Say, let us consider this way, it has been just compressed like this. It is just pushed into water like this. This is all water what we are having. Then you can surely understand this distance, what is the push you have given, that we can consider it as displacement in the vertical plane, that is y. And when you consider the same, even here also you will be getting the same value of displacement y. So, y is now going to be the displacement by means of which we have pushed that floating body into that water or that liquid. Now, here you should understand some data. Area of cross section of the body, you consider that one to be A, and vertical displacement, I just consider that one as y, and of course density of the liquid in which the body is floating, I just consider that one as rho. Then what one should understand in this case is, the portion initially the body is in equilibrium. Body in equilibrium means what is the condition over here in the case of fluids? The weight of that portion whatever is dipped inside the liquid and the buoyant force whatever that is acting in the upward direction, both are equal and opposite. Thereby the total system is definitely said to be in equilibrium. But in this case, what is happening? Since we have pushed it further deep into that liquid and leaving that one, it is now oscillating in the vertical plane. So, what is going to be the restoring force? What is now going to be the restoring force? Restoring force is nothing other than the buoyant force that is acting on that portion which has been dipped into the liquid now. So, the restoring force, when I consider F or S, that is now the buoyant force that is acting on this much of portion which has been dipped into the liquid. So, we now can understand this is nothing other than V rho G. That value of V refers to the volume, rho refers to the density, and G refers to acceleration due to gravity at that place where we are just performing this experiment. Now, one can understand here this volume can be written as base area into height. Height is nothing other than the vertical displacement of that body, into the value of rho, into the value of G. So, you can understand now this is the restoring force that is acting on that body right now. This gives you acceleration of that oscillating body. Acceleration of that oscillating body now becomes restoring force divided by the mass. Already we have calculated what is the restoring force over here. It can be written A rho G into minus Y by M. I can write it like this. Once again, this is exactly similar to the basic principle of simple harmonic motion, that is omega square y or omega square into minus y. We can just compare this equation with this. So, this implies what would be the angular frequency. Angular frequency omega now becomes root over A rho G by M. The moment angular frequency is this much, what would be its time period now? The time period when we calculate it as t, 2 pi under root m by A rho G. Similarly, what is its linear frequency? Suppose if they ask you, that can be written as reciprocal of time period 1 by 2 pi under root A rho G by M. So, whenever a body which is floating in a liquid is just pushed a little into that liquid and left, then the oscillations whatever it is making in the vertical plane also are going to be simple harmonic. And one can even calculate what would be its angular frequency, what would be the time period, and what would be its linear frequency for those oscillations what it's making there. So, this is another example where once again we come across the concept of simple harmonic motion.